We're going to take a look now at a couple more problems, 2D problems relating to triangles and circles and so on. So the first of these we're going to take a look at, we're going to take a look at question 8c. So question 8c involves circles inside a circle that sits inside the triangle, and then another circle sitting outside that. That's a pretty bad impression of what's going on in question 8c. So you're told that the circumference of the Earth, so that's the Earth in the middle. So we're told what the circumference of the Earth is, so we should know that the circumference is 2 pi times the radius. So if we're given the circumference, which is 40,075 kilometers, so 2 pi r equals 40,075, then you can divide by 2 pi to get what the radius is. So we're not going to do that. Alright, so you can work that out. So it's that many kilometers. Now, the thing we're told about these 3 points here is that they form an equilateral triangle. And in order to do this, what you need to see is that if you have an equilateral triangle like this, and you have a circle sitting inside it, then if you start breaking this up, you start drawing a line up there perpendicular. The first thing is that we know that these are all 60 degrees, right? 60, 60, 60. And if you start drawing lines into the center, then that's going to be 30 degrees there, because that's a right angle. That's going to be 60. I know this radius here, so either the sine rule or SOHCAHTOA can find me this distance here, which is in our diagram up here, that distance, which is the distance from the center of the Earth to the satellite, which is the radius of that outer circle, which is called the circumcircle. And it also tells me this distance here, which I can double to find the distance between each of the satellites. So the distance from this satellite to this one, this satellite to this one, and this satellite to this one, because it's equilateral. So the main thing to spot in this question is that we are looking at 30, 60, 90 triangles when we break this thing up like this. Alright, and once you've spotted that, it shouldn't be too bad finishing off the question. You can find this length, you can find this length. You can also then find, if you look at back here, it's easier to see that the height the satellite is above the Earth is that distance there. So if we've already found this distance down here, and we know this distance is the radius of the Earth, we should be able to find that height there. So we should be able to do everything from there. So that's question 8. That's the kind of the single observation that makes question 8c work. Right. Moving on then to question 9c, there's going to be a similar kind of an observation here. So what we have here is kind of like a gear for bikes. So you have a common tangent like that. And they've drawn in this handy dotted line for us, and they've called that E, and that's A, B, C, D, and F. Right. The two main things we're asked, the area is quadrilateral, so it's four-sided figure here, and then also this shaded area in here. Alright. Just to point out where we want to go with this, just point out a couple of things. The first thing is, if we want to find the area that quadrilateral, it's most handily broken up into a triangle and a rectangle. The reason we notice there's a rectangle is that this is a tangent to this circle here, so that means this is 90 degrees. It's also a tangent to this circle here, so that means that this is 90 degrees. And we construct the line to E so that CE is parallel to AB. So that means we have a parallelogram. The angles are all 90 degrees, so therefore it's a rectangle. So because that's 9, because it's a rectangle and that's 90 degrees, that means this is 90 degrees as well. So in order to find the area of the quadrilateral, we need to find the area of this rectangle. So that means find this distance and find this distance here, which is the radius of the small circle. We need to find the area of the triangle, which means find this distance and find that distance. Now this is the distance between the two centers, so that's the sum of the radiuses. This distance here is the whole big radius, take away that bit. But if you think about it, if this is a rectangle, then that is the same as that. So this distance is the big radius, take away the little radius. So keeping all that in mind, the big radius is 9, the little radius is 3, so this is 9, this is 3, this is 3, this whole thing here is 9, this is 3, so it's pretty clear that this is 6. Alright, back in a second. So we have this set up now. We should be able to find the area of this triangle. Oh, hang on, we need to find that distance there. Well, if we take out this little right angle triangle, that's 6. That distance there is 12. That's a right angle. We should be able to find that distance x. So that's the distance there. So once we have that, we can find the area of the rectangle, find the area of the triangle. Perfect. The second bit of the question asks us to find the shaded area here. So that's the area of the quadrilateral. Take away this sector here and this sector here. So in order to do that, what we need is we need to find this angle. Let's call it alpha, or what's that? Theta. So this angle theta here. And once we have this angle, that's 90, so we can find this angle here. This is also 90, so we can find the whole angle there. Alright, so if you remember from I think the first video, the area of a sector is equal to pi r squared theta over 360 if theta is in radians. So once we find the angle theta, we can find the area of this. The radius is 9, that's our angle. We can find the area of this. Alright, the radius is 3 and our angle is 90 plus whatever that bit is there, the bit that's left over. So the last thing that remains is to find the angle. So once again we can look back at this as a right angle triangle, which we've redrawn kind of badly over here. So if this is our angle theta, that's the hypotenuse because it's across from the 90 degree angle, which is there. So that's the hypotenuse. If this is theta, that's the adjacent. So looking at SOHCAHTOA, the one that has adjacent and hypotenuse is cos. So working from this then, cos of theta is equal to adjacent over hypotenuse, which is 6 over 12. So theta is the inverse cos of 6 over 12, which is half. So you go in and you find out what that is. Once you have theta, you can fill in the rest of the angles here. You can find the area of that sector, find the area of that sector, taken from the area of the quadrilateral. Alright, so each of those is straightforward enough once you get started with them. Alright, let's take a look at question 10c is a little trickier, and then we go back to question 5. So, question 10c. Okay, you're given in question 10c, we're given this diagram. We have the Earth, we have the core of the Earth, which I suppose is molten, and you have this, the path of a seismic wave traveling through the Earth from near the surface A to a monitoring station at B. Alright, so we're given the radius of the Earth, so we're given that distance OA, and the radius of the Earth, and the path of this wave is a circular arc of radius 29.1 units. Okay, so let's have a look, let's draw this out. So there's the Earth, there's the core, there's A, there's B, there's this arc coming in. Now there's one important bit of information that's missing on the diagram, and that is the center of this huge circle here. So let's say this huge circle has a center over there. Now this radius, so the radius from here to here, that distance, the radius of, that's the seismic wave there, so the radius of the arc that the seismic wave is traveling in is 29.1 units. The radius of the Earth is 6.4 units. Well, if that's 29.1 units, it means that there is 29.1 units as well. Because that's an arc, right? So you can think, if you put the compass, you put the center of the compass here, you extended the compass out to there, and started drawing the seismic wave coming through, right? So that's 29.1, well that's 29.1 as well, to there. Okay, so from the center, where the little finger is over here, so from the center to the point A, that's 29.1. Now, because the thing is symmetrical, we're told that AOB is 104 degrees. Well, that means that this angle in here is going to be half of 104 degrees. So that angle is going to be 52 degrees. So let's redraw out, that's O, let's call this C. Let's just redraw out that triangle. So the triangle we're interested in is AOC. So redrawing it out down here. Doesn't have to be exactly correct, or to scale. So that's 52. That's O, that's A, that's C. We're not sure what this is yet. The reason we're not sure what this is that that's the distance from C to O. So we know that from C to this bit is 29.1, but we don't know what that is, that extra bit there, and that's actually the radius of the core. That's what we're going to be looking for in a minute. Alright, so this is 29.1. This is 6.4, it's the radius of the Earth. If we could find this distance, right, that would be this whole distance, we could take away 29.1, and that would give us the radius of the core we're looking for. So we'll call this X, because we're looking for it. Now you have two options here, because we don't have right angle triangle. Okay, now this line up here, from here to here, that's not a tangent. We're not told it's a tangent, we can't assume it's a tangent. It isn't a tangent. So we can't use any right angle triangle theorems. So we've either got to use the sine rule or the cosine rule. Now we can use the cosine rule, because we have two sides, we want the third side and one angle. Remember, the cosine rule has three sides and one angle, so three sides and one angle, perfect. Or we could use the sine rule twice. To do that, these two match up obviously, so we could use this side to find this angle here. So sine 52 over, well, let's have a look at how we do that. Let's do it by the sine rule. Let's start it off. Right. So you've got sine A over A, sine B over B, and the first thing that we're going to do is we're going to find, let's call it theta. We're going to find theta there. So the reason we're putting the angles on top is that we're looking for an angle. It just makes the algebra a little bit easier. So sine 52 over 29.1 is equal to sine of theta all over 6.4. Because we want theta, we multiply both sides by 6.4, so you get 6.4 by sine 52 over 29.1 equals sine of theta, which is whatever that is. Stick it into the calculator, do an inverse sine, and you get what the angle theta is. Once you have theta, you can find the third angle by adding these and taking them from 180. And once you have that, you can do the sine rule again to find what x. So x over sine of this is 29.1 over sine of 52. And that tells you what x is. The other way that you could do it, and it probably won't fit here, is the cosine rule. So let's go on to a new page. So you can use the sine rule twice, or you can use the cosine rule. Now the cosine rule is a squared equals b squared plus c squared minus 2bc cos a. The thing here is that this is the angle A because it's the only angle that I have. So this is the matching side. So this has got to be the side A when I'm going to do my cosine rule. And what that means is that I'm not going to end up with dx over here. Dx is going to be on the right hand side. Alright, so when I go to fill that in, a squared is 29.1 squared is b squared, so we'll say 6.4 squared plus x squared minus twice 6.4 by x by cos of 52. So let's get out the calculator and work out what that is. So the left hand side, 29.1 to be squared, so that's 846.81 equals 6.4 to be squared, 40.96 plus x squared now twice by 6.4, 2 by 6.4 by cos of 52. So that's minus, let's say 7.88 x. Okay, now this is a quadratic in x, so get everything to the right hand side. So you got your x squared minus 7.88x plus 40.96 minus 846.81. So you better work out what that is. That's your constant. You're going to need a equals something, b equals something, and c equals something. And you use the minus b formula. It'll give you two answers. One of them will make sense as the answer for x. So one of them will make sense as this side here, and the other one won't. One of them might be negative, one of them might be less than 29.1. You know that this is, from the picture up here, you know that this side here is at least 29.1 plus a bit more, so it's bigger than 29.1. So if your x is less than 29.1, you can discard that answer. So either the sine rule or the cosine rule will work for that. The point is to draw the diagram and fill in on the diagram what's missing in the diagram you're given, and what's missing is kind of the rest of that circle. You don't need the whole circle, but what you do need is the center. Alright, so find x, and then coming up here, if you take away 29.1 from x, you'll get the core, and the core obviously should be less than the radius of the earth, hopefully. If it's bigger, you know you do that. Alright, so the last thing we're going to take a look at, the last of these 2D problems, is question 5c. Alright, so the main thing in question 5c, the main thing to see at the start is that if you've got an incircle like that if you look at these triangles here, right, join the incircle to each of the three corners, then that's the radius of the incircle there, that's the radius of the incircle there, and that's another radius of the incircle. Okay, and these are all perpendicular because it's the incircle, it's a tangent to all the sides, so where it meets the sides, right, if you join a line from the center of the circle to the point where it meets the side, then that's a right angle. Okay, so if this is the length A, this is the length B, and this is the length C, then, whoops, then instead of getting the whole area of the triangle all at once, you can get the area of this triangle, and this triangle, and this triangle. This one is going to be half the base by the height, this one will be half the base by the height, this one will be half the base by, so you think of this as the base, and then that's the height. Think of this as the base, and then that's the height, this is the base, and then that's the height. Okay, so that's part one. Part two involves, so you're given A, B, and C in terms of P and Q. So A is equal to P squared plus Q squared, B is equal to P squared minus Q squared, and C is equal to 2PQ. you're asked to show that it's right angled, what you do is you square each of them. So square that, right, write it out twice, multiply it out, square this, write it out twice, multiply it out, square this, write it out twice, multiply it out if you need to. And show that when you add two of them, you get the third one. Right? So whichever two you add, they're the small size, and the third one then, that's your hypotenuse. So we're going to assume that we're able to do that, and it should turn out that A is the hypotenuse. Alright, so A squared equals B squared plus C squared. So we're going to have a look at part 3. So part 3 says show that the radius of the in center, show that the radius of the in circle of the triangle in part 2 is a whole number. So we're looking to find the radius. Well, let's go back to part 1. Part 1 said that the area is equal to half the radius into A plus B plus C. But if it's a right angled triangle and if A is the hypotenuse, right, if that's A and that's B and that's C, then the area is also equal to half C by B, or B by C, whatever way you want to write it. Okay? So what we're going to do is we're going to put these two equal. There's not really anything else to do. The fact that the area came up in the first one suggests that we're going to use the area. We know that it's a right angle triangle, that makes it a lot easier to find the area. A is the hypotenuse, so it's half B by C. So we're going to put these equal, and because we were told we're dealing with this triangle here, we're going to replace A with P squared plus Q squared, B with P squared minus Q squared, and C with 2PQ. So a half times the radius into A plus B plus C is a half times BC. We can multiply both sides by 2, which will get rid of the halves for us, which is great. So the radius into P squared plus Q squared, B is P squared minus Q squared, and C is 2PQ, is equal to B, which is P squared minus Q squared, into 2PQ. So what we want to do at this stage now, and I'm not going to finish it from here, you want to try and cancel whatever you can here, divide across whatever's left inside in this bracket, you divide both sides by it, and hopefully it'll cancel with whatever's over here, and you'll end up with the whole number for R. Basically, we'll end up with the whole bottom, whatever bottom line we have over here, will cancel with whatever's on the top line. That's the plan when we're doing it. Alright, so we'll leave that there. Hopefully be able to finish that off. Like you can see straight away here that this is cancelled. So divide across by whatever you're left with. Factorize the bottom if you can. Factorize the top if you can. Cancel as much as possible, and hopefully everything on the bottom line will be cancelled.